This is Free Range Digital Design Foundation Modeling, Chapter 26, Lecture number 3. So we've been talking about counters, we've been using them in example problems. Now we are going to look at one more use of a counter, which is essentially an event counter. So this is the foundation module for a counter. Typically we have data coming in, data coming out, not always for either of those. So the data coming in is data that we can load into this counter. Once we load it into that counter or latch it into the memory in that counter, remember it's a register, that data appears on the data output. We can have various control inputs to a counter as well. We can clear the counter, which means we can put all zeros into the storage of the counter. Typically clear is usually asynchronous signal, but you can design it either way. You can state it either way, either as synchronous or asynchronous. Load is a control signal that causes this data in value to be latched into the counter. Up and down and hold have to do with the count. Up increments the count, down decrements the count, and hold doesn't change the count. Typically we have a clock, of course, because it's synchronous. As far as status goes, we have a ripple carry out. The ripple carry out indicates when the counter has reached its terminal count, which means when it's counting up, there's n ones, and when it's counting down, there's n zeros stored in this counter. The status outputs generally feed into the inputs of the state machine. The state machine reads those, decides what to do, and sends out control signals, typically to the control inputs of things like counters. There are typically two main uses of counters in digital design. One is to time events, to do things a certain amount of time, and we've seen that with the ripple carry out. We've done things like such as 15 or 16 times. Ripple carry out turns on, it indicates we're done doing those things. The other thing we're going to use a counter as is an event counter, which means it's counting an event. So event might happen every clock cycle, might not happen every clock cycle, might happen synchronously or asynchronously, but anyway, you're going to be counting events. Typical uses, just counting things such as events or counting things just to time something. The event counter is equivalent to an accumulator where you're always adding one, so I thought I'd draw that real fast. This is an n-bit register. What I'm doing is taking the output of that register, feed it into this ripple carry adder, and adding 1 to it. So what I've done here is grounded one of the inputs, but put a 1 on the carry-in, which means I'm always adding 1 to the value that's stored in this register. So this is an accumulator event counter, equivalent to a counter that increments. This is an example problem. This is an example problem. It says design a circuit that counts the number of times the value 47 hex appears on the circuit's input, and essentially it happens on the press of a button. So it evaluates 10, 24 consecutive clock edges, and it has two outputs, which is the count and an LED, essentially an LED saying that the circuit is counting. What's going to happen is the button is pressed and it starts counting the inputs, 1 per clock cycle. Every time it sees 47 on the inputs, it increments a counter. And so we can go ahead and write this down. Two outputs here. It has a button on the input to get it started, and it has, we'll just say, 8-bit data input. The count here is the number of times it sees the number 47, which means and I'm going to look 1024 times, so it's tempted to say 1024 is 2 to the 10th, but you have to realize that 2 to the 10th, the biggest number I can get with 10 bits is 1023. So this can't be 10. It has to be 11 because all 1024 of those values might be 47, which means I need 11 bits to encode it. So this is my final top-level black box diagram. So let's do this circuit. I have to have two counters in the circuit. One is an event counter. It's counting the number of times it sees 47. The other one is just the counter counting how many different values it looks at. So there's two counters. One's used as an event counter, and one is just used to do something X amount of time. a clear input. We're going to need to clear both of these. I have another counter. This is my event counter, and I don't need an RCO. We agreed that it's 11-bit output, and the up input is going to be a special input. We're going to leave that to be controlled by the state machine. What else we need in this thing is a way to figure out if we got 47 on the input. That is going to be a comparator. A is going to be data, doesn't really matter, it could be B. Certainly I need to draw a state machine, FSM, and so what's going to control this? Generally speaking, this is a status input, this is a status input. Both the EQ and RCO are status inputs. So this is the event counter, it doesn't need an RCO. We're okay with that one. Certainly we got to clear here. We can clear both these counters, and so clear is a control signal, and up is also a control signal. This is clocked. I think I forgot to put a clock in the last problem. Good enough for now. If I forgot something, I could fill it in. What's happening here is this circuit is waiting for button press. When there's no button press, I don't have to do anything. Okay, so if someone presses a button, I have to do something. So in this wait state, what I want to make sure I do is turn the up off. I don't want it to be counting while it's in the wait state. So I also have to handle clear in both of these states. These clears are both outputs of the state machine. Here's this one. I've handled up. I have to handle clear. Now what's going to happen is when this button is not being pressed, I'm not clearing it. When someone presses that button, I'm going to turn the clear on. So once again, I am using this as a Mealy machine. I'm designing this as a Mealy input because in this state, in this wait state here, I've got clear. Sometimes it's a 1 or it's asserted, sometimes it's not asserted based on the button input. This next state, we'll call it count, a nice self-correcting name. And I'm going to stay in this state until I get an RCO. So as long as I don't get an RCO, I stay in this state. And so what else do I need to do in this state? I need to handle both these outputs here. I want to make sure it doesn't clear, but what I want to do here is say if EQ is asserted, I want to count up on this thing. Otherwise, I want to hold it. So let's put that in here. We'll say up. God, I think I'm almost done with this. I need to handle this other output here, and it's not RCO not. It's RCO. And I'm just checking this over, see if I've got everything here. So I've handled up and clear in both states. I think it's good. Now notice what essentially in this state right here, in this wait state, RCOs that don't care, I don't really care about it. And essentially in this count state, buttons that don't care. I could put it in the state diagram, but it messes it up. I don't need to put it in there. So what's going to happen is it's going to stay in this state. Anytime those values are equal, it's going to assert this count, this up input. It's going to cause this counter to increment. So we need to put that in here. We also need to say clear asynchronous. We've used it as a Mealy output, so it needs to be asynchronous. And what else do we need in this thing? Check through this thing, make sure I don't forget anything. And I'm going to call it done. Now, last thing here is how this is controlled. So here's control inputs controlled by the state machine. Up input is essentially an internal control, so this is once again, this is the internal signal. The clear and the ups are coming from the state machine for that circuit controlled, and that is all we have. Now we could have done this as a Moore machine, but it makes less sense because essentially it would cause me to divide this state into two states, which I don't want to do. It kind of clunks up the problem.